All right, welcome back for more action. Here is Check Your Understanding, the practice problems. I decided to make a video for this because we would usually do this in class, but because I want to have you guys working in groups in class, you can do this one at home. In the boxes below, draw a force diagram for each of the situations. Draw each force as a vector, direction and magnitude, from the dot representing the object. For each situation, determine if the net force on the object is 0 or not, and if each object will be accelerating or not. Use a ruler. Okay, so a book on a table. Well, is there gravity? Absolutely. So I'm going to have the force of gravity down, but it's not accelerating down, it's just sitting on a table. So there must be something equal and opposite in the other direction, and that is the normal force. Are the sum of all forces equal to 0 or not equal to 0? Well, in this case, they are equal to 0 because there's no acceleration. Okay, number 2, a box is being pulled by a rope and it's accelerating in a forward direction. Friction is non-negligible, which means there is friction. So let's see, it's a box and it's on Earth. So it's going to have a force of gravity downwards. It's going to have a normal force upwards because it's not accelerating in the y direction. However, it has a pulling force pull or force applied, and since it's accelerating in the forward direction but it has friction, then I must have just a little bit of a friction vector back here, and I call that the force of friction. Are the sum of all forces equal to 0 or non-zero? These are non-zero, so F is equal to ma. Really, the sum of all forces is equal to mass times acceleration. Is it accelerating? Yes. Well, it says it's accelerating in the description. Silly, come on. A hockey puck is at rest on ice. Sum of all forces equal to 0? Betcha, because I just have the force of gravity acting on the hockey puck. And I have the normal force acting on the hockey puck. Is it accelerating? No. A hockey puck is traveling to the right with a constant velocity on frictionless ice. Ooh. Let's see. Well, it's still on Earth, so it has a force of gravity. Line that up in the center a little bit better. Check this out. A good move. Force of gravity is down. Force normal is up. Hockey puck is traveling to the right with a constant velocity. Well, constant velocity means no acceleration, which means no net force, or no sum of all forces. So the sum of all forces are still equal to 0, even though it's moving. But it's moving at a constant velocity, so that means no acceleration. Is it accelerating? No. It's at a constant velocity. A picture hanging from the wall by 2 ropes. So this one, we'd have 2 forces of tension, and really, this one you would draw it as on the actual picture first, maybe. So I would have a force of tension here. I would have a force of tension here, and then I would have the mass times gravity here, so the force of gravity here. If I was to expand that and just put it on one dot, I would look like I have the force of tension up, and I have the force of gravity down. Tension can be either written as big T or FT, and force of gravity. Is it accelerating? No, so the sum of all forces is equal to 0. There we go. A soccer ball flying through the air on the way to the goal, no air resistance. If there's no air resistance, it would have a force of gravity down. And that's it. Here the sum of all forces would not be equal to 0. And it would be accelerating the downward direction. And is it accelerating? Yes. Okay, here we go. F equals ma. Weight equals mass times gravity. So this is weight. This is mass. And this is gravity. We're going to actually round up to 10 for this. Notice F equals ma and W equals mg are really the same thing, except g is a special type of acceleration and weight is a special type of force. So the units for weight are in newtons. The units for gravity are meters per second squared, as shown right there. Good, warm up. Force is measured in newtons, and mass is measured in kilograms, and acceleration is measured in meters per second squared. If we know the force exerted on an object in newtons and we know the mass of an object, we can easily find the acceleration of the object experiences by dividing the, let's see, A is going to be equal to sum of all forces divided by mass. So sum of all forces divided by the mass. If we know the force exerted on an object in newtons and we know how fast the object accelerates in meters per second squared, that should be up there, then we can easily find the mass of the object experiences by dividing, let's see, sum of all forces divided by acceleration would be equal to mass. Sum of all forces by the acceleration. If we know the mass of the object in kilograms, we know the acceleration of the object experiences, we can calculate the force, mass times acceleration. Practice problems. Oh, so here we go. A net force of 25 newtons to the right is applied to a 12 kilogram mass. What will be the acceleration of the mass? Well, what do I know? I know that a force is equal to 25 newtons. I know that it has a mass equal to 12 kg, and I'm looking for the acceleration is what I don't know. Well, I know that acceleration is equal to force divided by mass. I've got my equation. Now, let me show you my work. That's going to be equal to 25 divided by 12. What is that, 2.5? 25 divided by 12 on my calculator, 2.08. 2.08, it's an acceleration, so it's meters per second squared. I've got my work, and I've got my correct answer with units right there. Beautiful. Next, a net force of 60 newtons is applied to the left of a 2 kilogram mass. What is the acceleration of the mass? Sometimes you can draw a little picture. And say I've got a force pushing from the left. It's going to go that way. 16 newtons. The mass is 2 kg. And I don't know my acceleration. Well, I know my acceleration is equal to sum of all forces divided by the mass. That is my equation. Check. My work is 16 divided by 2. Check. And my answer is going to be 8 meters per second squared. Boom. Next, a shot putter. That's the guy that throws the heavy balls. Exerts a net force of 140 newtons on a shot, giving it an acceleration of 19 meters per second squared. What is the mass of the shot? Well, let's see. What do I know? I know that the force is equal to 140 newtons. I know that the acceleration is equal to, I know the acceleration is equal to 19 meters per second squared. And I'm looking for the mass. Okay, well, I know that mass is going to be equal to the sum of all forces divided by acceleration. I could have sum of all forces here as well. That is my equation. Let's show you my work here. My work is going to be 140 divided by 19. 140 divided by 19 is equal to 7.37. 7.37. It's a mass, so that must be in kilograms. So I've got my correct answer with units, and of course I showed you my work. And I think, you know what? I think that's all I'm going to show you for this one. I think you are good for the rest of these problems. You should be able to do these on your own. For the Atwood's machine, I want you to try this one on your own based on what I showed you during the 3.1 definitions and equations. That's all I'm going to put in the video. However, I will fill out this answer sheet for the rest of these. Hopefully that gets you started, and good luck. I look forward to seeing your learning.